Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video, we are going to be dealing with electric field part 2. Now remember that in our previous video, we dealt with part 1. So today we'll be dealing with the part 2 of it. So get your pens and paper ready. Do not go anywhere, I will be right back. You are welcome back to my school YouTube channel. Like I said earlier, we are going to be dealing with electric field part 2. So as usual, before we begin with our lesson, let's quickly run through the objective for today's video lesson. So objective number 1, at the end of this video, we should be able to state Coulomb's law. 2, calculate the electric field between two charges. 3, explain electric field intensity and electric potential. 4, explain the term capacitance. 5, calculate the equivalent capacitance for a series and parallel arrangement capacitors. So let's begin with our lesson. So before we state Coulomb's law, let me quickly just run through what we did in our previous video. So in our previous video, we actually saw the meaning of electric field. So I'm just going to go through it again. Okay, so an electric field is a region of space where a charged body experiences an electric force. And in our previous video, we said that electric field is a vector, meaning that it has both magnitude and direction. And we also said that the electric field can be represented by electric lines of force. So let's kick off with Coulomb's law. So Coulomb's law states that the electric force F between 2 point charges Q1 and Q2 separated by a distance R is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. So mathematically, here F is directly proportional to Q1 and Q2, okay? And also F is inversely proportional to the square of R, okay? And this is referred to as inverse square law. So combining these two equations together, equation 1 and equation 2, we'll be having F being directly proportional to Q1 and Q2 and inversely proportional to R square. Of course, this is just a relationship, it's not an equation, okay? So to make it an equation, we have to introduce a constant, okay? So introducing a constant, then we'll be having F being equal to K, Q1, Q2 all over R square. So K here in this equation is a constant of proportionality, and it is equals to 1 over 4 pi epsilon naught, okay? And epsilon naught is also a constant called permittivity of free space. So in place of K, if we replace it with 1 over 4 pi epsilon naught, we'll be having F being equal to 1 over 4 pi epsilon naught times Q1, Q2 all over R square. Now remember here that the value of 1 over 4 pi epsilon naught is equals to 9.0 times 10 raised to power 9 Newton meter square per Coulomb square. Now remember that this is also equal to the value of K, okay? So the value of K is also equal to 9.0 times 10 raised to power 9 Newton meter square per Coulomb square, since K is equals to 1 over 4 pi epsilon naught. Let's move to the next slide. So F is the force that either charge exerts on the other. It is either a force of attraction or that of repulsion, okay? And this is actually what separates or what differentiates electric field from gravitational field. For gravitational field, the force is always that of attraction, but for electric field, it is both attraction, or it can be attraction or that of repulsion, okay? So when the charges are the same, that is when the charges are like, the force is that of repulsion, as you can see in the diagrams below. So here we have a positive force, and here we also have a positive source. So there is repulsion between both forces. Then below we also have another diagram where we have a negative force and we also have a negative force. Or let's say the charge there is negative. So the force between them is that of repulsion, since the charge are the same. So on the other hand, when the charges are opposite, that is unlike, the force is that of attraction, as you can see in the diagrams below. So here we have negative, okay, and here we have positive. Then the force between them is that of attraction, because when the charges are opposite, then the force is that of attraction. Okay, the same as the diagram below. We have positive and negative, so the force between them will be that of attraction. So in both cases, the force on one is equal and opposite to the force on the other. So irrespective of whether the force is negative or positive, right, the force on one, okay, is also equal to the force on the other, but opposite to the force, okay, but opposite, right, in the case of attraction. In fact, in both cases. Okay, so let's move to the next slide. So here we are going to be discussing about the resultant force on charges. Okay, so when three forces are distributed such that their centers form the vertex of a triangle, as you can see below, then the resultant force on any one of them can be obtained by means of vector addition, and shown below. Okay, so here in this diagram we are considering the charge, that is, we are considering the positive charge. Okay, so here we have a positive charge, but here we have negative charge, and here we also have negative charge. You will see that the positive charge Q1 is attracted to the negative charge Q2 and also attracted to the negative charge Q3. Let's move to the next slide. So the diagram of forces on Q1, that is the positive charge, is as shown below, right? So since the positive charge is attracted to the negative charge Q3, okay, while here the positive charge is also attracted to the negative charge Q1, okay? So this is going to form a force with a force of F2, and here with a force of F3. So F2 and F3 are the forces on the positive charge Q1, and F is the resultant force on the positive charge Q1, okay, as you can see in the diagram above. Now, basically what we are trying to do here is to find the resultant of the force, or the resultant of the force on the positive charge Q1, right? So, but remember that F2, which is electric force, okay, is equals to 1 over 4 pi epsilon naught Q1 Q2 all over arrow 2 square. That is, the arrow 2 square here is the distance between the positive charge Q1 and the negative charge Q2, okay? While for F3, the electric force, okay, which the negative charge Q3 attracted the positive charge Q1, is equals to 1 over 4 pi epsilon naught, then Q1 Q3, okay, over arrow 3 square. So the arrow 3 is the distance between the positive charge Q1 and the negative charge Q3. So to calculate for the resultant, we simply take the square root of the square of F2 plus the square of F3, right? And for us to calculate the angle formed, then that will be F2 all over F3. Now remember that this line, okay, is also parallel to this line. So for us to calculate for theta, of course, we need to apply tan in that case, because here we have opposite, which is F2, and beside here we have F3, right? So, and remember that tan is equals to opposite all over adjacent. So in this case, we'll be having F2 all over F3. Hence, tan theta is equals to F2 all over F3. Let's move to the next slide. Also, given that three charges are distributed, okay, as shown in this diagram. So the positive charge is repelled from the positive charge 2Q with a force F1. It is attracted to the negative charge minus 2Q with a force F2. So the resultant force on the positive charge Q is F. So here we can calculate for F1. So for F1, we'll be having it to be equals to 1 over 4 pi epsilon naught, then 2Q, okay, 2QQ. Now the 2Q represent the positive charge 2Q being repelled, okay, that repelled the positive charge Q1 all over the distance between those two charges, which is arrow square. Okay, then for F2, we also have it to be equals to 1 over 4 pi epsilon naught, then 2QQ. Okay, so the 2Q here is for the negative charge minus 2Q. Then the Q is the positive charge Q all over the distance between those two charges. Let's move to the next slide. So we can see that F1 is equals to F2. Now remember that for the two charges we have plus 2Q and minus 2Q. So they are equal, okay, but opposite. Okay, so in that case they attracted the positive charge plus Q by the same amount of force, right? So since F1 is equals to F2, their resultant will bisect the angle between them. F is simply the sum of the component of F1 and F2 in the direction of F. Okay, so F is equals to F1 cos theta plus F2 cos theta, so that F is equals to 2F1 cos theta since F1 is equals to F2. Also from the diagram, cos theta is equals to 1 over 2D all over arrow, and this is equals to D all over 2 arrow. Okay, so let's talk about electric field intensity, E. So electric field intensity can also be called electric field strength. Okay, so electric field intensity at any point in the field is defined as the force per unit charge at that point. Okay, so the direction of the field strength is that of the force on a positive charge. Thus, electric field intensity is a vector. That is, E is equals to F all over Q, where F is electric field, Q is equals to electric charge. Therefore, F is equals to EQ, of course, by simply making F the subject of formula here, okay, by cross multiplying. So if we cross multiply, F will be equals to EQ, okay. So let's move to the next slide. Now consider a point charge Q, capital letter Q, in a vacuum. If a test charge Q is situated at a distance arrow from Q, as you can see in the diagram below. So when we talk about test charge, we are just referring to an imaginary vanishingly small positive charge, okay, that is used to detect the presence of an electric field. Okay, so from thus F is equals to 1 over 4 pi epsilon naught, then capital letter Q, small letter q, all over arrow squared. So we are just talking about the force of attraction between the capital letter Q, okay, and the small letter q. Of course, the force of attraction here is that of electric, okay, but remember that E, which is electric field intensity, is equals to force all over F all over Q, right? If we decide to substitute 1 over 4 pi epsilon naught, capital letter Q, small letter q, all over arrow square in place of F, okay, we'll be having 1 over 4 pi epsilon naught times capital letter Q, small letter q, then Q arrow square, okay? So basically this is it. More or less like you have 1E is equals to 1 over 4 pi epsilon naught, then Q, capital letter Q, small letter q, all over arrow square, then divided by Q. Of course, what will happen is that this Q will become the denominator. So that E will now be equals to 1 over 4 pi epsilon naught, then point Q, capital letter Q, small letter q, all over Q arrow square. Okay, so that is how this formula came about. But E is now equals to 1 over 4 pi epsilon naught times Q all over arrow square. So the small q here, we cancel out the small q here. So that will be having E to be equals to 1 over 4 pi epsilon naught times capital letter Q all over arrow square. Okay, so if we put this together, we'll be having E to be equals to capital letter Q all over 4 pi epsilon naught arrow square. Okay, so the unit of E, which is electric field intensity, is Newton per Coulomb. If the charge were surrounded by a material of permittivity, let's move to the next slide. Epsilon, instead of being in vacuum, then E is equals to Q all over 4 pi epsilon arrow square. So the epsilon here without any subscript is referred to as absolute permittivity. Okay, so here are some examples for us to put some of all these formulas we have seen into work. So let's begin with question 1. The force between two identical charges P and Q is 4.2 times 10 raised to power minus 2 Newton. If the magnitude of each charge is 2 microcoulomb, calculate the electric field due to P at the point where Q is situated. So in order for us to solve this question, we are going to move over to the board to do that. Okay, so first thing first is to write out the parameters that are given to us in the question. First of all is for us to identify what we are asked to calculate for. So we are asked to solve for the electric field, okay, due to P at the point where Q is situated. So the electric field E, okay, due to P where Q is located, okay, is given as E is equals to F over D. Okay, so here we are told that the force between the two charges P and Q is equals to 4.2 times 10 raised to power minus 2 Newton. So here it's supposed to be Q, not D, okay? And we're also told that the magnitude of each charge is 2 microcoulomb. So Q is equals to 2 microcoulomb, okay? And which is equals to 2 times 10 raised to power minus 6. So micro here is actually referred to times 10 raised to power minus 6. So here will be C. So we just substitute so that E is equals to, so we just substitute these values into the given formula. Here we'll be having E to be equals to 4.2 times 10 raised to power minus 2 all over 2 times 10 raised to power minus 6. Okay, so here 2 here is 1, 2 here is 2, and 2 here is 1. So we'll be having 2.1 times 10 raised to power minus 2 all over 10 raised to power minus 6. Right? So here we can apply the law of indices for the 10 raised to power minus 2 and the 10 raised to power minus 6. So here we'll be having 2.1 times 10 raised to power minus 2, then minus 6. Of course, remember that minus automatically changes to plus. So that we'll be having 2.1 times 10 raised to power minus 2 plus 6. And this will be equals to 2.1 times 10 raised to power 4 Newton per Coulomb, okay, since we are talking about electric field intensity, okay. Due to P at the point where Q is located is equals to 2.1 times 10 raised to power 4 Newton per Coulomb. So let's return back to the screen to solve the remaining examples. So example 2. The plates of a parallel plate capacitor 5.0 times 10 raised to power minus 3 meters apart are maintained at a potential difference of 5.0 times 10 raised to power 4 volts. Calculate the magnitude of the I electric field intensity between the plates, II force on the electron. So we are told that the electron charge is equals to 1.6 times 10 raised to power minus 19 Coulomb. And let's move over to the board to provide answer to this question. So the first thing first is to write out the parameters, okay, that are given to us in this question. So E is not given to us, that's what we are looking for. But in this question, we are given D to be equals to 5.0 times 10 raised to power minus 3 meters. And we're also given V, okay, which is the potential difference to be equals to 5.0 times 10 raised to power 4 volts, right? So to calculate for electric field intensity here, we use E is equals to V all over D. Of course, this formula, I'm going to be deriving it as the lesson progresses. Okay, so this is another formula that you can use to calculate for electric field intensity. So let us substitute the values that are given to us so that we can get the value of the electric field intensity between the plates. So V is given to us to be equals to 5.0 times 10 raised to power 4 all over, now D is given to us to be 5.0 times 10 raised to power minus 3. Okay, so 5 will cancel out 5. So that we'll be having 1.0 times 10 raised to power 4. Then here for the 10 raised to powers, we just apply the law of indices. So here we'll be having minus minus 3. Okay, so minus will automatically change to plus. So that we'll be having 1.0 times 10 raised to power 7. Okay, volts per meter. Okay, so this is the value of the electric field intensity between the two plates. So let's solve the second question, which is II. So for the II, we are asked to calculate for the force on the electron. But remember, we are giving electron charge to be equals to, so 1.6 times 10 raised to the power minus 19 Coulomb. Okay, so that is the value of the electron charge. But remember that in the first question, we actually calculated for electric field intensity. So we already know electric field intensity. And there is a formula connecting electric field intensity, force, and charge. And that is E is equals to F all over Q. So since we know this value and this is given to us, we can calculate for F. And F here represents the force on the electron. Okay, so we just cross multiply. So here we'll be having F to be equals to EQ, that is E times Q. Now remember, E here stands for electric field intensity, while Q here stands for the charge, that is the charge on the electron. So F here represents the force on the electron, which we are asked to calculate. Okay, so here F now equals to, so we have actually solved for this. So this will be 1.0 times 10 raised to the power 7, then times 1.6 times 10 raised to the power minus 19. Okay, so 1 times 1.6 is still 1.6. So here we apply the law of indices. So here we have times 10 raised to the power 7, then plus, then minus 19. Since the two 10s are multiplying each other, okay, so according to the law of indices, we simply take one of the base and then add the powers, right? So here we'll be having this to be equals to 1.6 times 10 raised to the power. This will be equals to minus 12. Because we're having 7 plus minus 19, right? So that will be minus 12, okay? Minus 12 Newton, okay? So the value of the force on the electron is equals to 1.7 times 10 minus 12 Newton, okay? 1.6 times 10 raised to the power minus 12 Newton. So let's return back to the board to continue to solve example 3. Okay, so for example 3, the diagram below illustrates two collinear electric charges of magnitude plus Q and minus Q. The charges are equidistant from a point P at which a test charge is placed. Okay, remember that a test charge is a positive small charge. Okay, and that charge is vanishingly small or infinitesimally small. Okay, so let's move to the next slide to see the diagram. Okay, so this is the diagram. So we are asked to copy the diagram and use arrows to indicate from the point P the direction of the electric force F1 due to plus Q, then II, electric force F2 due to minus Q, and III, electric field intensity E. Now remember that P here is a positive charge, okay? So let's move over to the board to provide answer to this question. Okay, so this is the diagram that is given to us. So here is P, here is plus Q, and here is minus Q. So if you look at the two charges, they are equal but opposite. So in that case, the arrows that you use to indicate, okay, the direction of the forces too will also be equal, okay? So here, this is positive, okay? The test charge here, P, is positive. So P is going to be repelled by plus Q, while P is going to be attracted by minus Q. So our diagram is going to be like this. Okay, so this is our plus Q. Let's say this is where our P is, right? So the diagram, this P here is going to repel the force, right? While this minus Q here, okay, is going to attract Q. Okay, so we just make sure the two arrows are equal in length. Okay, the diagrams are equal in length. So this is going to do this with F1, and this will do this with F2, right? And remember, the force between the angle between these two forces is equals to theta, right? Now, the electric field intensity is represented by the line, okay, that bisects these two forces, or like the resultant of these two forces, okay, represents the magnitude, okay, represent the electric field intensity, okay, and this electric field intensity is parallel to the distance, okay, between those two charges. It's parallel to the distance between those two charges. Okay, let me shift this downward a little. So that's okay. So here is Q plus. So let's put here for Q minus. Okay, so this is our E. Okay, so this is just the answer to this question. So the electric field intensity is parallel to the distance between the two charges, that is the positive and the negative charge. But since the two charges are equal, right, then the magnitude of the forces too will also be equal in length. So just take note of that. While the resultant of both forces represent, okay, the electric field intensity, and it should be parallel to the distance between the two forces. So this is the answer to question number 3. So let's return back to the screen to continue with our lesson. So what we have on the board represent the answer to question number 3. So on the board there you can see F1, which is answer to I. Then you can also see F2, which is answer to I. Then you can also see the E, which is answer to I. Okay, now remember that the resultant of the two forces F1 and F2, okay, is equal to the electric field intensity, okay, and everything was indicated on the diagram. So this is where we draw the curtain for the preview of today's video. You can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, we'll talk about electric field flux, we'll also talk about electric potential. Then we'll also discuss about capacitors and capacitance. We'll also talk about the different arrangement of capacitors in circuit and more. Okay, so I believe you enjoyed the preview of this video. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next videos.